similarly, you have this Smith chart tool also. So this Smith chart utility here resembles the same way as you have your Smith chart at your hand and you try to design the circuit. You know the source impedance on the Smith chart, you know the load impedance on the Smith chart, and then you try to design impedance matching using reactive loads, whether inductive or capacitive or resistive, maybe some at some times. Okay, so what happens? Uh, you have to calculate all those things in using your transmission line theory. You find out the value, you find out where it is going, what is the electrical length, and what is the impedance value it will give after you use it for a specific transmission line length. Here everything is automatic. For example, if you notice, I have started this, so the frequency is 1 gigahertz, so you can define the frequency. You can define your source impedance. For example, if it is a SMA port termination like this design, you can keep it 50, and then clicking it normalize, it will normalize the loads by dividing everything to 50, every impedance to 50. So you can either have normalize or just leave the normalize here. This is your network schematic. Right now you have ZS and ZL. Your ZS is defined to be 50 ohm, but your ZL can be any value in this particular Smith chart. And let me have a random value, complex value. For example, I say 100 plus J20. Okay, enter. So now you see this is your one source impedance and this is your load impedance. You can see load is squared. Okay, so you see the square one is for load, the circle one is for source. So these 2 points are there. Now the next thing is to use the elements to reach up to this particular point. So I have my ZL. I can lock these impedances so that it will not change now. I cannot change it now. And now I want to design. So I have selected this ZL and now I need to have a capacitive or inductive element to reach to 1. So here are these elements in the palette again. So you can use inductive elements, you can use conductive elements, you can use transmission lines in conductive or reactive, in any reactive configuration so that you reach to this particular source impedance. So for example, I am interested in using transmission line. So I have selected this transmission line. So this is series transmission line, not any stub. These two are stubs. So once I take this transmission line, I can see based on the electrical line length of the transmission line, which you can see here. So here it is 0, I am at the same point near 0. Now I am increasing the degrees and likewise I am moving on the Smith chart. So I can either drop this point here or I can have a transmission line length till this. So for example, I keeping it minimum electrical length transmission line, I select to go up to this point. So the next is either reactive, either capacitive or inductive. So I am taking this, but I cannot reach. Let me use this to see if I am able to reach to 1. So there is not, so both of these elements are not following this as we know. So what I can do, I can drop it anywhere and it gives me another flexibility. I just move it. So with this very convenient approach, I can design the whole circuit, which is giving me matching based you can see in on the graph here. So this graph shows stop frequency up to 2 and start frequency 0. So the center will be 1 and this maximum is actually 1. So this is for the uh, reflection coefficient magnitude. As you can see, if I do it in dB and keep maximum 0 and if minimum minus 50, so it is 0 axis, it is minus 50 axis, just to keep you similar to what we see in ADS. I am using it in DB. So the maximum is 0, the minimum is minus 50, and the plot is S11, trace 1 or trace 2, whatever. Type is DB. So here you can simply, by selecting these components without even figuring out, without even any calculation, you get these transmission line element, or I would say a complete impedance transformer, to transform this complex impedance of 100 plus J20 into 50 ohms. And with your convenience, you don't need to calculate anything. You know the parameter of this transmission line, Z, and it is the theta. And then this is another transmission line with characteristic impedance and electrical line length. Okay, so I hope this is cool for you guys. I mean, just select the load impedance and source impedance, and you can simply design the transmission lines, the impedance transformer network using this Smith chart utility. So this is the use of this Smith chart utility, which is very handy. You can directly, now you have built the circuit, so you can directly bring it to the ADS schematic. For that, you have these options here. So build ADS circuit. This auto two element match is for two element match, which we already did here. So you can do the matching on your own and then build ADS circuit. No smart component available. So for that, so what it says, place a smart component from the schematic palette. So you just click here. This clicking here will give you a smart component in your circuit schematic. Just select it here. Oh, okay. So for example, I don't wish to use this network. I am using this 50 ohm port, and we know, so C control V. What was the load impedance? The load impedance was 100 plus J20. So let me write 100 plus J20. So once I do this, I will be selecting the smart component here. So it says the schematic. You have this schematic here, test. So the test is here, and it automatically took this Smith chart smart component. So this is smart chart component, DA Smith chart match one, DA Smith chart match one. So once you do this, build ADS circuit. So now this particular symbol actually have the circuit which you have designed here. And how do you see that circuit? So you just simply select it and go to this push into hierarchy. So you see here 50, 62.22, 50, 62.22, and 50, 52.62. 50, 52.62 ground circuited stub, short circuited stub, short circuited stub. I am popping out from this hierarchy. So now if I simulate it, I should get the similar performance as I am getting in my Smith chart, right? So I have simulated, you see 0 to minus 50, and you are getting that result. Cool. So this way you can design the circuit using Smith chart utility. The impedance transformer circuit for any impedance, either you can change the source also, it is not like you cannot change it. So for any source and load impedance, you can design this impedance transformer using this Smith chart utility. This will be very quick to use. And to use that smart component, just click on this particular palette. You will get it here. Use it. Once you use it, in the drop down, it should be available if you have selected the correct schematic. Okay, so this is another thing which I wanted to tell you. Now, if there is anything else you can ask, or we are good to close this session today.